Hello, dear students. Good morning, good afternoon, and good evening. Anytime you are watching this lecture, welcome to a new lecture on discrete mathematics. Matrices are widely used in many applications. They help us in linear equations. So in this lecture, we will learn about matrices. How we can define a matrix? It's a simple rectangular array of elements, right? So you can say this one is like one matrix. It is 2 by 2 matrix. In here, we show a matrix by number of rows and number of columns. We normally show number of rows by m. For example, 1, 2, then we say m equals to 2. And also we show the columns by n, and we say n is equal to 2. So we call it as, this is a m by n matrix, which is 2 by 2 matrix. A matrix with the same number of rows and columns is called as square matrix. And two matrices are equal if they have the same number of rows, one thing, same number of columns, and the corresponding entries in every position are equal. This is a matrix. So we have 1, 2, 3, m equals to 3, and 2 n equals to 2. So we say it's a 3 by 2 matrix. We say that the number of rows is m, and number of columns is n. Then this is one m by n matrix. We call each element A 1 by 1, means A is in row number 1, column number 1. A is row number 1, column number 2. A is row number 1, column number n. In here, A is in row number m, column number 1. In here, A is in row number n, column number n, right? So we can say, for example, for if I is equal to 1, then this is the first row, this is the second row, this is the m row. And also we can call the columns of each matrix. We have too many types of matrices. Like row matrix where m is equal to 1. Then we call it as row matrix, right? As you can see, we have only one row, but we have n columns. So rows 1 and columns n, many columns. We may have, on the other hand, column matrix. In here, B, it should be m, right? M equals to 1. No, sorry. N equals to 1 and number of rows is m, right? So we have one column but m rows. This is the opposite side of the row matrix. We may have null matrix. If all the elements are 0, then we call it as null matrix. We also have singleton matrix. If you have only one element, right? So m is 1 and n also is 1, only one element. If the number of rows and columns of a matrix same, then we call it as square matrix, like 2 by 2, 4 by 4, right? 3 by 3. This is called as a square matrix. Number of columns more than number of rows, it is rectangle. If number of rows more than number of number, then it is vertical. So if, for example, this one, 1, 2, 3, 4, 5, 6, this is a rectangular. But if you have this one, 1, 2, 3, 4, 5, 6, this is vertical. In diagonal matrix, all components are 0 except those in diagonal. As you can see, these are not 0, but the rest are 0. So Hij in matrix H, where Hij is equal to 0 if I is not equal to 0. They are 0, other they are not 0. Scalar matrix, all the principal diagonal components are equal. So Kij is equal to Kji. In here they may be different, but in here they are same. In identity matrix, a diagonal matrix, there all are 1. You can see here. If we divided this matrix into two triangles, then if the lower side is 0, we call it as upper triangular matrix. If the upper one is equal to 0, then we call it as lower triangle matrix. So these elements are all 0, these elements are all 0 in here. This is the difference between upper triangle matrix and lower triangular matrix. Let's talk about arithmetic operations on matrices. We can add two matrices together. Suppose we have a matrix of A and elements are shown by Aij, and another matrix we have B, Bij, and they are m by n matrices. So if we want to come up with the sum, we just simply show A plus B and we do summation of each corresponding element. Very easy. If this is A matrix, if this is B matrix, then this is A plus B. What we did, 1 plus 3 equals to 4, 0 plus 4 equals 4, minus 1 plus minus 1 minus 2, 2 plus 1, 3, 2 plus minus 3 minus 1, minus 3, 0, minus 1, 3, minus 1, 2, 4, 1, 5, 0, 2, 2. Very simple, right? But you should remember they should have the same size. If they don't have the same size and two matrices are different in size, we can't do summation. How about subtraction? If we have matrix A and matrix B, and again if they are n by n, so in here with subtraction we show A minus B. If this is A, if this is B, the sum which is A minus B is simply Aij minus Bij. It means the subtraction of each corresponding element. A minus 3 minus 2, 0 minus 4 minus 4, minus 1 minus minus 1 0, 2 minus 1 1, 2 minus 3 5, minus 3 0 minus 3, and the last. The next operation that we are gonna try on matrices is multiplication. If we have two matrices and one is A and another, if this A is n by k, n number of rows, k number of columns, and B is k by n, right? As you can see here, the number of columns of second one is equal to the number of rows and opposite side. Then the product of A and B, just we show like this, A, B, is one matrix of m by n. M by n, and each element is equal to the sum of products of the corresponding elements in one row multiply column. In other words, we can say if you have A here, B here, AB is Cij. What is Cij? Cij is A of, it means the element in the first, so we are going for I and J. The first column, row I, multiply the first row in column J. And we do the rest to find it. Let's see one example. If this is A and this is B, we want to find A, B. This is the first row, right? We just multiply the first column. It means 1 multiply 2 plus 0 multiply 1 plus 4 multiply 3, 14. We do the same thing for the next one. Next row, multiply the first column. Third row divided by this one. Fourth row divided by first column. Then again, first row, second column. Second row, second column. Third row, second column. Fourth row, second column. Finally, you can come up with this A and B. So here is a notation of matrix multiplication. For example, if we want to do for this row, just we multiply by this row, right? And this is what we want. Cij AI1 B1j plus AI2 B2j plus up to Aik Bkj, which is, so this one multiply this one and summation will come to this. Here is another example. If this is A and this is B, if we do multiplication, A multiply B is this one. And opposite side, if we do B multiply A, these two are not same. So we come to conclusion that A multiply B in terms of matrices is not the same as B multiply A. In a scalar, we say 4 by 5 is equal to 5 by 4, right? But in here, we can't say they are not the same. But in terms of summation, it doesn't matter. A plus B equals to B plus A. Sometimes we need to find out the determinants of matrices. The determinant of a matrix is a scalar value, which is a function of the entries of a square matrix. So it should be square, 2 by 2, 3 by 3, something like that. The number of rows and columns should be the same. How we do it? If we have a matrix of, for example, if A is equal to A11, A12, A21, A22. So what we do, the determinant we show like this or like this, same. These two are determinant. Is, for this matrix, you know, we show like this. Is this one multiply this one minus this one multiply this one, right? For example, if this is our matrix 2, 4, 6, 3, 2 multiply 3 minus 4 multiply 6, which is equal to minus 18. Finding the determinants for big matrices is very difficult. In this case, we need to find cofactors. Cofactors of Rs for each element of A is theta Rs minus 1 in power of R plus S. And determinant of R and S. What is R and S? If this is our matrix, when we say R and S is R equal to 1, S equal to 1, it means we do not consider this row and this column. We consider the rest, right? So this is the meaning of R and S. Here is an example how to find determinant for a large matrix. This is our question, right? Just we learn here. So you should remember one thing here. Then this is for first row and second row, because 1 plus 1 is 2, so it will be positive. But if it is 2 and 1, then it will be negative of that one. So let's see this example. This is 1, 3, 2, 4, 5, 6, 8, 7, 9. We will go for this one, right? the first one is to remove this one and this one. So the rest will be this, right? Then if we remove this one, okay, and this one, the rest will be 4, 6, 8, 9. Why minus is here? Because of here. Because this, for the first one, it was minus 1 in power of 1 plus 1, so it was 1. But in here, it is minus 1 in power of 2 plus 1, it is minus 1. That's why this negative is here. We do the same for all the rest, and finally we will come up with this one. When we come here, for any row of I, what we do? Just this one, multiply this one. So 1 by 3 plus 3 by 12, and 2 by minus 12. So the determinant is 15. For any column J, 3 multiply 12, for example, 5 multiply minus 7, and 7 multiply 2, 15. In this way, we can find the determinant. In scalar algebra, a number times its inverse is equal to 1. Right? In matrix algebra, we must find the matrix of A minus 1 for A1 where become to identity matrix. In this case, we need to find out adjoint. Adjoint of a matrix we show by ADGA is a matrix of cofactors transposed. Transposed means changing of rows and columns. So, adjoint of matrix A is transpose of cofactors. It means theta RS prime, which is based on our equation minus 1 in power of R plus F, and determinant of RAS, this transpose. So, inverse of a matrix is, we show by A in power of minus 1, 1 by determinant A, adjoint of A. Here is an example in order to understand matrix inversion. If our matrix is this one, 2, 4, 6, 3, we will find the inverse of an order of 2 and 2. So, in here, we first must calculate determinant for B. So, B is 2 by 3 minus 4 by 6, which is equal to minus 18. We can write down the matrix of cofactors for B, and then we transpose to get the adjoint. So, adjoint B is equal to theta B transpose, which is 3 minus 6 minus 4, 2, and we will come with this one. So, using this formula, we can come up with this one. Then we can go for B inverse, which is the determinant and disjoint. We can now write down the inverse of this B. B inverse is 1 by 18, scalar multiply the matrix, right? Which is this one. 1 by 18 multiply this one multiply minus 4, this one multiply, and this one multiply. Then, we find out the inverse. So, the inverse of this one is simply this one, right? 3, 4, 6, 3 is minus 3 by 18, 4 by 18, 6 by 18, 2 by minus 2 by 18. If you want to make sure that whether your answer is correct, just do a simple multiplication, right? So if you do the multiplication, as you can see here, it will be minus 3, 18, 4, 18, 6, 18, 2, 18. So this will be 0, this will be 0, and this is seems to be identity. How about power of matrices? Like in scalar, we have x squared, 2 squared is equal to 4. 5 squared is equal to 25. 2 power of 3 is equal to 8. How about matrices? Can we do the same thing for matrices? Yes. If we have a square matrix like A and we have a positive integer k, then A in power of k, a matrix in power of an integer, positive integer, not negative, positive integer, then it is simply k copies of A. A multiply A multiply A multiply A. How many times? K times. For example, if this is our square matrix A, 4, 0, minus 3, 7, we want to find out A square. It is very simple. A multiply A. You can see here. So, 4, how we can do it? 4 multiply 4 plus 0 multiply minus 3, which is equal to 16. Then, first row, next column. 4 multiply 0 plus 0 multiply 7 is equal to 0. Next row, minus 3, 4 plus minus 3, 7 is equal to minus 3, 3. And minus 3 multiply 0 plus 7 which is equal to 49. How about A in power of 3? Very simple. This one multiply this one, right? So A multiply 2A. Or you can say A multiply A square is A3, right? Very simple. You can come to this one. Some slides ago, we had the terminology of transpose. Transpose is simply changing lines by columns. If we have a matrix of A, and we show by Aij, it is a n by n matrix, then the transpose we show by At is, this is n by n, right? This transpose is n by n. Just we change, interchange the rows and columns of a matrix. So in here, Bij equals to Aij. For example, if our A is 2 by 3 matrix, 2 rows, 3 columns, then the transpose is 3 by 2. You can see 2 columns, 3 rows. Just we change it. 1, 2, 3 become 2, 1, 2, 3 in column. 4, 5, 6 become 2, 4, 5, 6 in column. This is called as transpose of A. The next topic is symmetric matrix. We need to have a square matrix A. In previous slide, we learned how to find transpose. If a transpose of a matrix is simply equal to itself, then it is a symmetric matrix. A symmetric matrix if it is square and it is equal to its transpose. If A is a matrix of I and J, it is symmetric if Iaj is equal to Aji. Why? Because here is the term of transpose. When we do transpose, we change line by column, right? So it means we change Ij to Ji, right? For example, here you can see this row is equal to this column. This row is equal to this column. This row is equal to this column. That's why A is equal to AT. It means this is a symmetric matrix. Symmetric matrices do not change where their rows and columns are interchanged. It means they remain the same. The next one is 0, 1 matrices. A matrix all of entries are either 0 or 1 is called as 0, 1 matrix. Algorithms operating on discrete structure represented by 0, 1 matrices are normally based on Boolean arithmetic. That we already learned about this Boolean arithmetic. And or P1 and P2 if both are the same. Both are the same and 1, otherwise 0. In OR, so this is simply AND operation. This is simply OR operation. If one of them are 1, 1. If both of them are 0, 0. This is the meaning of Boolean operation that we already learned. The same thing can be applied for 0, 1 matrices. The next one is join of 2 matrices and meet of 2 matrices. If we have A, which is composed of A, I, and J's, and another matrix of B, which is B of I and J's, and if they are M by N, and they are 0, 1 matrices, because they have only 0 and 1, then we define join of A and B, or you can say A or B, then the 0, 1 matrix with AIT or. The same in meet we do with AND. Simple, right? The meet and join. An example help you to better understand the topic of join and meets. You already understand these operators for scalars. In here we do for matrices. If we have 2 matrices, A is equal to this one and B equal to this one. Join is simply OR. 1 or 0 is 1. 0 or 1, 1. 1 or 0, 1. 0 or 1, 1. 1 or 1, 1. 0 or 0, 0. And simply meet is AND. AND. Right? So 1 and 0, 0. 0 and 1, 0. 1 and 0, 0. 0 and 1, 0. 1 and 1, 1. 0 and 0, 0. This is the definition of joins and meets for 0, 1 matrices. You should remember that this is applicable to 0, 1 matrices, not for all. The next one is Boolean product for 0, 1 matrices. If we have a matrix of MK, number of rows, columns, and B, K, and N, then the Boolean product shown by A circle dot B. A circle dot B is M and N 0, 1 matrix where Ci and J is AI1 and B1J or AI2 and B2J up to come here AIK and BKG. This is Boolean product. Here an example to understand this one. If this is one matrix A and this is one matrix B. So what we do, if you remember in the previous slide, we say Cij equals to AI1 and B1J or AI2 and B2J up to coming at the end of AIK and BKJ, right? So we follow this equation 1 and 1 or 0 or 0. 1 and 1 or 0 and 1. 1 and 0 or 0 and 1. So what we do here, 1 and 1 is 1. 0 and 0 is 0. 1 or 0 is 1. So this comes to here and this comes to here. Then we have the next 1 and 1, 1. 0 and 1, 0. 1 or 0, 1. Right? 1 and 0, 0. 1 and 0, 0. 0 and 0, 0. 0 and 1, 0. 1 and 0, 0. 0 or 0, 0. 0 and 1, 0. 1 and 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1 or 0, 1, 1 and 1, 1, 0, 0, 1, 1 and 1, 1, 0 and 1, 1 and 0, 0, 0, 0, finally 0. This is Boolean product of these two matrices, Boolean product. These are two main properties for 0, 1 matrices. The Boolean product, as we learned here, of any matrix with I is equal to A, right? And the opposite side is the same. It doesn't matter if we change it. But if you remember, A, B was not equal to B, A. But in here, same. But we say that A plus B equals to B plus A based on those properties. But for identity matrix, it happens. Okay, so here, if we have this matrix A, B, C, D, E, F, G, H, I, if you do all together, finally you will come with the same. And it's the proof that A Boolean product with I is equal to A. In order to do Boolean powers for 0, 1 matrices, if we have A as a square matrix of 0 and 1 matrix, then we have R as a positive integer, then the Boolean power, we say Rth Boolean power of A is the Boolean product of R factors A. We denote by this one. So very simple. Rth Boolean power of A is equal to A Boolean power of A up to R times. Here is an example. Here we have 0, 0, 1, 1, 0, 0, and this one. So we want to do, for example, for 2, right? If you do it, it means this one multiply itself, Boolean product, right? So if you do, then you will come with this one, right? If you do 3 times, it means this one by this one. Finally, if you do 5 times, then you will come to this one. That for n, if it is n more than 5, remains the same. It means A of 6 equals to A of 5, right? Remains the same. And the last topic is how we can use matrices in order to solve system of equations. What is the system of equations? For example, here we have 3 equations. Equation number 1, equation number 2, and equation number 3. How many variables do we have? Variables are x, y, and z. How we can solve this one using matrices? Matrices are particularly useful when we want to solve system of equation. This is the coefficients. It means this is 1, 2, 1, 3, minus 1, minus 3, 2, 3, 1, right? So simply 1, 2, 1, 3, minus 1, minus 3, 2, 3, 1. And this is a set of our variables, set of variables x, y, z. And here there are the other side 3. So very simple, we say that A is matrix of coefficients, x variables, and this is the other side. Ax equals to B. We can say that A inverse of Ax equals to A inverse of B, which implies x is equal to A inverse of B. So if this is our A, and we do based on what we did already for inverse, we can solve system equation by computing the inverse of A. And then we multiply it by B. B already we have here. So once we find multiply by B, and our matrix A and its inverse is what we did here, then we can simply solve it. This simple multiplication, we will come to 3 minus 2, 3. So it means x is equal to 3, y equals to minus 2, and z equal to 4, right? So if you do that, you will find that 3 plus 2 multiply minus 2 plus 4 equals to 3, 3, 0. As you can see, it is correct. So in this way, we can use matrices in order to solve system of equations. So this was a simple introduction about matrices. Please study and please also try to practice based on the examples that we have here. And also you may try to find some other examples from the book. So this will help you to better understand the topic. Please feel free to ask me if you have any questions. You can send your questions by email or ask me during the class. Thank you.